Okay, so in the last video we ended with a discussion of T and B frames, which even if you don't remember the term T and B frame, that's okay. It's what you need to know from that is the unit tangent vector, which we've already been working with, and we've defined that, the unit normal and the binormal. So here we have a space curve, and we have used this space curve before. I think we did an arc length problem with it, if I remember correctly, previously in this section. We're going to use this same function but for a different purpose. We want to find t, n, and b for this function at a specific point, 1, 0, 0. As before, anytime we're being asked to work with a vector function at a specific point, we want to determine what parameter value will take us to that point. And by inspection, I can see that t would equal 0. It shouldn't be too hard to convince you that it's 0. So we'll make a note of that. Now, what do we need in order to find all of these? Well, we're going to start with t. T is r prime over the magnitude of r prime. So let's get r prime of t. R prime is going to be negative sine of t, cosine of t. And remember, when we did this before, this becomes sine over cosine, which is just tangent of t. Okay? Now, in that previous example where we did arc length, remember we found the magnitude of r prime because that's in our arc length formula. That would be sine squared plus cosine squared plus tangent squared. Remember, this is equal to 1, and 1 plus tangent squared is secant squared. Taking the square root of that would just be secant. Technically, again, the absolute value of secant, but I'm not including the absolute value here simply because I know that when I eventually get to the point that I'm finding, t, n, and b specifically, I'm plugging a 0 in. 0 lives in the first quadrant of the unit circle where secant's already going to be positive anyways. So leaving that absolute value off is going to make a world of a difference when we have to evaluate more derivatives down the line. Okay, so what is t? There is some trig here, pretty straightforward trig, but it's some simplifying that you have to take care of. So remember, t is negative sine of t, cosine of t, tangent of t, divided by that magnitude we just found, secant of t. Okay, which again is the same thing as dividing each component by secant. Well, negative sine over secant is the same thing as negative sine of t times cosine of t. Cosine of t over secant of t is the same thing as cosine squared. Tangent of t over secant of t. And I think I actually made one little mistake here. I just want to correct that really quick. This shouldn't be tangent. It should be negative tangent, right? Because derivative of cosine is negative sine. So this would have been negative sine over cosine, negative tangent. Doesn't affect anything here, but it does affect that right there. So negative tangent over secant of t is negative sine of t, which is easy to derive just by simplifying that trigonometric expression. So there's t. Okay. Now what do we do with that? Well, eventually we're going to find the unit tangent at this point. And I could do that right now just by plugging 0 in, but I'm going to wait until I have everything else that I need and then do t, n, and b all at the same time. Well, I'll do t and n at the same time and then b after that. So in order to calculate n now, we need t prime. So let's find t prime. T prime of t. So that means we're taking the derivative of this guy right here. Okay, not too difficult. Product rule right here. I'm going to get sine squared of t minus cosine squared of t from this using the product rule. Chain rule right here. I'm going to get negative 2 cosine of t, sine of t right there. And then right here, I'll get negative cosine. Okay, this I can simplify by remembering my double angle identities. Cosine squared minus sine squared is cosine of 2t. So if I flip the order, sine squared minus cosine squared, that's negative cosine of 2t. Here, 2 sine cosine is equal to sine of 2t. Putting the negative in front, I get negative sine of 2t. And then finally, I don't need to simplify that negative cosine anymore. Okay? All right. Now, in order to find n, Remember, n is equal to t prime over the magnitude of t prime, so now we need that magnitude. Well, that would be equal to the square root of cosine squared of 2t plus sine squared of 2t, let's make that a little bit longer, plus cosine squared of t, or square root of 1 plus cosine squared of t. And no, that's not going to get much simpler. There's not a trig identity that I'm going to use to make that any simpler. If it were 1 minus cosine squared, that'd be a different story, but it's not. So that tells me that n of t is equal to negative cosine of 2t. Remember, this part up on the numerator is going to be t prime, so that's negative cosine of 2t, negative sine of 2t, negative cosine of t, and we're dividing that by the square root of 1 plus cosine squared of t. So let's find t and n now at this specific point where t is equal to 0. Okay, looking at t, we have negative sine, so we're plugging zeros in for the t's here. The sine here, that's going to make this go to 0. This will also go to 0. This will be 1 squared, which is just 1. So that means t of 0 equals 0, 1, 0. What about n of 0? Well, here's my formula for n. If I plug a 0 into everything, I'm going to get negative cosine of 0, so that's negative 1. This will be a 0. This will be another negative 1. If I plug a 0 in down here, I get root 2. So putting everything together, that's negative 1 over root 2, 0, negative 1 over root 2. Now we're not done, but sometimes it's helpful at this point, just to make sure you didn't make some calculation error somewhere, that you are in fact getting unit vectors. Remember, t, n, and b are all supposed to be unit vectors. So if you took the norm of both of these, you would see that they come out to 1 in both cases. All right, last thing, let me box these off because these are answers. Now we need b, and remember, it's b of 0. So this is something that you can do that's going to save you some time. It's tempting at this point to find b of t instead of b of 0, because we found t of t and n of t. The problem with that, though, is that those functions are relatively, t is up here, those functions are relatively complicated, t and n, and if we took the cross product of these two functions as they are, it'd be a gigantic mess, algebraically speaking, and it's just, there's no point, because it's not the binormal function that we're looking for, it's just the binormal vector for this one point. So this will equal t of 0 cross n of 0, or in other words, 0, 1, 0 cross negative 1 over root 2, 0, negative 1 over root 2. I'll let you work out the cross product by doing the the determinant and everything, but this one comes out to negative 1 over root 2, 0, 1 over root 2. So we're going to save a little time just by jumping straight to that answer. And there we go. Okay, once again, it is a unit vector, and it's even worth noting at this time that if I took the dot product of any pair of these, I should get 0, because remember, each vector in these three vectors is orthogonal to the other two. So their dot products should all equal 0, and they do. You can verify that pretty easily here. Okay. A little bit left to do, so a couple of terms that we wanted to find. If you have a space curve C, any point, let's call it P for now, any point on that space curve has actually three, but only two that we care about here, planes that are associated with it. One thing that's important to remember is that if you have any two non-collinear vectors, like these, then those two vectors will always determine a plane. It's the plane that contains both of them. Geometrically, it's not difficult to see why that's the case, and I think we've even addressed that back in chapter 12. But if we look at our T and B frames, T, N, and B, picking different pairs of those vectors and using them to determine a plane gives us two of these planes here. So the first one is something that we call a normal plane. A normal plane for a curve C at a point P is a plane that contains the n and b vectors, so your unit normal and your binormal. Let me actually draw a little picture of these on the back here. Ignore that stuff, that's from a different class. Imagine we have the space curve, right? Okay, if this is the point P right here, then the normal plane is going to look kind of like this. The curve is going to punch through that plane at a right angle. Okay, so imagine the space curve is piercing that normal plane at a perfect right angle. That's why we call it that. Okay. Also associated with point P is something that we call the osculating plane. Osculate, it means to kiss, and we use it in a word similar to the word tangent. So if the osculating plane of the curve C at the point P is the curve that contains the plane that contains the vectors t and n. The way you want to think of the osculating plane, if we come back here, is you imagine it as kind of skating along that curve. So on a two-dimensional surface like this is really difficult to show you, but this plane is sort of like skating along this curve in a sense of being tangent to that curve. So normal plane, osculating plane right there. Okay, now within the osculating plane is an important circle. We call it an osculating circle, and its definition has a lot of things to go through. So if you have a point P on a space curve, and if that point has curvature given by this, so if we know its curvature, then we define the osculating circle of C at P to be the circle that satisfies this list of things. It has to lie in the osculating plane of C at P, which we just defined up here. It has to have the same tangent as C at P, by like tangent line is what that means. It has to lie in the concave side of C, which is always going to be the direction that n points in. We didn't show that, but that is an important fact. And the radius of the circle is the reciprocal of the curvature. Now remember, we showed in a previous example that a circle of a given radius will have a curvature equal to the reciprocal of that radius. That's the reason we're using the reciprocal for the radius right here. Okay? So let's see if we can come up with, excuse me, an example where we want to find the normal and osculating planes of a given space curve at a particular point. We're going to reuse the previous example because, remember, these planes involve t, n, and b. And as we saw in this example back here, finding t, n, and b is a lengthy process. So it's nice to be able to use some stuff we already came up with. Okay, so let's start with the osculating, or no, normal plane. Let's do normal plane first. Normal plane. Which two vectors determine the normal plane? Well, it's the vectors n and b. Okay, that's nice. Now, what do we use to come up with the equation of a plane, n and b? Well, in order to come up with the equation of a plane, you need two things. Remember, this is from chapter 12. You need a normal vector to that plane, so you need a vector that's orthogonal to all of the vectors in that plane. And then you also need a point on that plane. Well, we have a point right here. It's a point on the space curve, but remember, the plane shares that point. So how do we come up with a normal vector to that plane? Well, let's go back to this picture that I drew up here. If these are the vectors n and b for our normal plane, then the vector t is orthogonal to both of those. So that third vector, the unit tangent vector, is automatically normal to that plane. We could use it as a normal vector. So I'm going to set my normal vector n equal to my unit tangent vector, which in the previous example we found was 0, 1, 0. Now all that's left to do is find the equation of that plane. Remember, if you have your unit tangent vector, it's the components times x minus 1. So this is it would be 0 times x minus 1 plus 1 times y minus 0 plus 0 times z minus 0 equals 0. Remember that? These two terms disappear. This just becomes y equals 0. So the plane y equals 0 is the normal plane for this space curve at that point. That plane is the same thing as the xz plane. Okay, so what that means is if we were to graph this curve, we should see this space curve punching through the xz plane at a right angle. That's what that would imply. Osculating plane. Okay. It's the next thing that we need. So same logic as before. What does the osculating plane consist of? It's the plane that's determined by the vectors t and n, right? So that being the case, we need a normal vector to that plane. But the binormal, b, is orthogonal to both of these, meaning it would be orthogonal to our osculating plane. It makes a perfectly valid normal vector to use for our plane. What was the binormal in this case? In that previous example, we said it was negative 1 over root 2, 0, 1 over root 2. Okay, so that means my osculating plane is going to be, and I'm going to skip all of this stuff because we can simplify this, So negative 1 over root 2 times x minus 1 plus, well, let's forget about the 0. It's just going to go away anyways. Plus 1 over root 2 z minus 0, or just z, equals 0. It's fairly typical in a case like this to multiply both sides by that root 2 there. In fact, I'll just multiply by a negative root 2 so that this first term comes out positive. That's going to mean we have x minus 1 minus root 2, minus 1. Let me fix that. It's going to be x minus 1 minus z equals 0. Or if I add the 1 to both sides, x minus z equals 1. Really, any of these would have been a valid answer, but this one seems to be like the simplest version of that. Okay, so that's your normal plane. Or sorry, osculating plane. We got an example of each type here. All right, last thing we had talked about up there before that example was the osculating circle, and it was a long list of properties that the circle is supposed to satisfy, but it may not have been a very clear picture of what that actually represents. So we're going to do an example that comes straight out of your book. We want to find the equation of an osculating circle to the parabola y equals x squared at the origin. Now, what the purpose of this circle is it's supposed to be the circle that best approximates the curve at a particular point. You notice this circle kind of fits really nicely into the origin part of that parabola. It just seems to kind of fit. And the reason for that is because, one, it's on the concave side, so it's going to be contained inside that little bowl shape. And the curvature of the circle matches the curvature of the parabola at that point. So both curves, the circle and the parabola, are changing direction at essentially the same exact rate at that point. Okay. If you were to look at the cover of your book, if you have a hard copy of the book, it's got a picture of a violin on it. And if you're using the 8th edition, which you should be for this class, you'll see little circles kind of sketched in there or drawn in with with software or something, kind of fitting into the different curves of the violin body. Those are osculating circles. So right on the cover of your book is where you're seeing this. So let's see if we can work this out. We want the equation of the oscillating circle here at the origin. Now, what we're going to use for this, because it's a plane curve and it's of the form y equals x squared, we can use that pull this up real quick. We can use that that other curvature formula that we came up with for plane curves specifically. So here it is just for reference. It's equal to the magnitude of f double prime. Well, actually, since we're using y, let me change the way that looks. It's going to be the magnitude of the absolute value of y double prime over 1 plus y prime squared to the 3/2 power, right? So we need y and y prime here. Or sorry, y prime and y double prime. Y prime is 2x. Y double prime is just 2. So plugging these in, y double prime is 2. Its absolute value is still just 2. And y prime is 2x, so this is going to look like 1 plus 4x squared to the 3/2 power. Okay, that's our curvature as a function. But what about at the origin? Well, at the origin, x is equal to 0. So really, we want to be plugging a 0 into that. That's 2 over 1 to the 3/2 power, or just 2. Okay? That means that the radius of our osculating circle should be the reciprocal of that. It should be 1/2. Okay? So with that in mind, where do we put this circle in the plane? Well, at this point, you kind of want to sketch it out. And I know I already printed the graph here with the circle already drawn in, but you would want to look at your parabola. So draw the, sketch the graph of y equals x squared. Think which side is the concave side. Well, that's the side that's inside the parabola. And the parabola and the circle should both intersect at the origin. So that implies that the circle is going to be opening up like this. In addition to that, by the symmetry of this parabola, it sort of makes sense that the osculating circle would be symmetric about the y-axis. And it's sitting on the same tangent of that parabola at the origin. So the tangent of the circle at the origin should be the x-axis, just like the parabola has the x-axis as its tangent there. All of that indicates that we're looking at a circle like this. Now, if the radius is 1/2, then I should be able to move up by 1/2 to find the center of that circle. And if I go up one more half, then I get a diameter of 1, and that's why we have this circle that has a diameter of 1. What's the equation of this circle, though? Well, if the center of this circle is the point 0, 1/2, that would, and the radius of this thing is 1/2, that would imply that the equation of this circle is x squared plus y minus 1/2 squared equals the radius squared, 1/2 squared, or 1/4. So that would be the equation for our osculating circle. And that's also going to wrap up 13.3.